Okay, good morning everybody. I hope everyone's having a wonderful day. So today we're going to be talking about a topic I'm really excited to talk to you about. It's quite a bit different than, well, it's actually not that much different, but it's still something that I would consider rather fundamental for algorithm design. And you can think of it as another data structures topic. So we're going to talk about so-called graph algorithms, and they center around a mathematical object called a graph. That dreaded M word. If you don't like the dreaded M word, you can call it a combinatorial object. That also works, unless you're not a big fan of combinatorics. But there's these things called graphs. And the main motivation behind why we're going to be studying graphs is that many problems that we study in computer science tend to get modeled as graphs. There was an old saying that one professor that I knew back when I was doing my undergraduate and so on, but I don't know him very well, but he had a very good reputation for always giving the following interesting quote. Is that if you have an interesting problem, there's likely a way you can model it using a graph. That's how fundamental, oftentimes, using graphs can be when modeling problems. And later on in this course, we're going to see more problems where we model them using graphs. So graphs are a much more general way of representing a problem than, say, just a typical, like, an array of length n, or even just a tree. So tree, this is going to be much more general than just a tree structure. It's going to be much more general, but some of the terminology is going to carry over from when we talked about trees. So what exactly is a graph? I want to motivate this with a couple of interesting ways you can think about things that you may encounter out in the real world. So the first one I thought I would show you is a series of servers. So these are servers here. And these right here, these fun monitors that look like they've melted in the microwave. Don't put a monitor in the microwave, by the way. Just don't do it. I'd recommend not doing that. The ones that look like they're melting, like they're just a little too hot today, these are my clients. And this would be an example of a computer network. So this is an example of a computer network, where, say, for example, you may have information at these servers, and these clients may need to request information from these servers. So that's an example of one thing that's out there that very often people deal with. For example, if you're interested in the internet, that's one such example of a network, but it's really, really big. This can be modeled with a graph. I'll talk more about that in a moment. Another one, this is one that people tend to run into. Say if you're traveling. Now, it doesn't necessarily have to be to airports. I know the timing of this is not the greatest, but you can imagine these, instead of being airports, so I've labeled some of these airports. For dramatic purposes, I needed the pointy stick. I have all of these different airports, and I have distances, which, well, in some graphs called weighted graphs, we have so-called weights, where we're going to put a number on that edge. So it's going to be kind of like a tree where I had edges in a tree. We're going to have this concept of an edge again, but it's going to be far more general. So I'm going to have distances between my airports. Say this is how much the distance is between the two airports. And maybe, for example, I would like to figure out what's the shortest route from one airport to another port. Say if I want to go from Vancouver all the way to the East Coast. Or I want to go from, say, Vancouver to Winnipeg or Toronto. These numbers represent distances I could travel. Now, if you don't like this airport example, it could be just, say, your favorite walk in the park. And say these are your favorite places you'd like to go visit in the park. You could ask all sorts of questions about your trip. For example, what's the shortest path for me to get from, say, the start entrance of the park to, say, the dog walking area? Or say you can even ask more interesting questions than just that. You can ask questions that have killer applications in logistics, such as, hey, look, say if I have all of these places I want to visit each one exactly once without repeating myself twice in my trip. Problems like that are much harder. We'll talk about an example of a problem that is very much like that later on. But these are examples of ways I can model using a graph. So this second example is a map of flight routes. See, these are flight routes with distances. Naturally, when you have a flight map like this, you might ask, okay, well, if I want to minimize the amount of fuel I use, say, in the aircraft, I may want to try to find a path that doesn't go as far, right? Yes, somebody pointed it out. Yeah, traveling salesman. Yeah, the traveling salesman problem. It's a classic problem in combinatorial optimization. If you're wondering, you're trying to bark up my alley and you start talking about things like this. This stuff gets me very excited. So, that being said, I want to tell you what a graph is. Now, in this picture, you'll notice that I have these things like the computers here, like the server, this client. I also have these airports. These in a graph are what we would call vertices or nodes. So this isn't too terribly strange because we've done something like this with trees. And we have these connections between the nodes we call edges. So we're going to adopt a model that allows me to describe relationships like these, and that's a graph. So let's get to the definition of a graph. This is our working definition. So we're going to see some more examples like these as we progress, and we're going to study several different problems on graphs. So today we're mostly just going to focus on graph terminology. So you may or may not have seen some of these things before. For those that have, you can lounge back and you can watch me talk about graph theory a little bit. So anyways, let's talk a bit about what a graph is. So I need to define that for you. So a graph is a pair VE. So V is the set of vertices. As I said when we were talking about trees, the singular for vertices is vertex, not vertexes, or it's just vertex for singular. Plural for vertexes and vertexes, it is vertices. Remember, like I said, it's kind of cringe, just don't do it. Or you could call them nodes if you'd prefer. And E is going to be a collection of pairs of vertices. So we would call these the set of edges. So most contexts, I'll call them edges, but sometimes in different circumstances, you may call them links. Like say, for example, if we're talking about a network like that, some people like to call them links. If we're talking about a so-called directed graph, we often will call the edges arcs or directed edges. So the graph is a rather general way of representing interconnections between different entities. And these entities would be the vertices, and the connections between them are formed by edges. So I'll be doing an example in a moment, but I just want, for the sake of clarity, because I want to sometimes say, oh, the number of vertices and the number of edges, I'm going to denote those as M and N. So N is the number of vertices, M is the number of edges. If you're wondering about these bars, these are for cardinality. So if you've done a little bit of set theory, you would know, oh yeah, when you put the bars up like that, it's just asking, well, how many elements are in that set? So I'm just going to call M the number of vertices, M the number of edges. And very often when we study and use graphs, there are different kinds of pieces to a graph. So the goal today is I'm going to show you a variety of different terminology and different ways we can talk about a graph. So classically, there are indeed edges. Like I said, they're pairs of vertices. And often, most broadly, they tend to be denoted with a pairing like this, without any context. Now, we call U and V the endpoints of edge E, or the end vertices of E. So if I say, oh, U and V are endpoints of E, then you know that the edge is UV. Some people like, by the way, some people, especially in graph theory circles, they like to, instead of writing it like UV with rounded parentheses like this, sometimes just write UV like this. That's okay. And depending on the kind of edge it is, sometimes there's other notations you can use to simplify things down or enforce meaning on things. So I want to give you an example of two different kinds of edges. So these are different ways I can model the relationship between my vertices. So the first example is the undirected edge, which I will colloquially refer to as an edge without any context. So if I say edge, I'm talking about an undirected edge. So the way you would think about it is if I have an edge from U to V or V to U, I have, say, two vertices like this, and then there's an edge that connects them. So often a convention is used, like, so notice that I can refer to this as an undirected edge, and I can use this notation with the rounded parenthesis notation like this. But I have to, every time I do this, I have to tell you, oh yeah, it's an undirected edge UV unless there's more context. Some people in some circles like to use curly braces to represent the fact that this is an undirected edge. What does that mean? Undirected simply means that the order of the vertices does not matter. For example, UV, this is no different than me writing the edge VU with the curly braces like this. In fact, if I wrote VU like this, the other way around, it doesn't matter. The order does not matter. It's an undirected edge. So it just represents the connection of U with V. So the order doesn't matter here. And often you'll find me use these curly braces just because you may be familiar with sets. And in sets, the order doesn't matter. That's where this notation comes from. So you can notice that I could write VU and it doesn't change anything, right? So you can use this, or if you want to say, oh, undirected edge E, then use this rounded parenthesis approach, that's also cool too. I'm not too terribly picky about these things, just as long as you're clear. Now, in contrast, there's another kind of edge called a directed edge. So we'll run into things called directed graphs, which I'll define in a moment, where what we do is we enforce an order on the vertices in the edge. So now you can think of this literally like an ordered tuple, where now the sequence I give you actually does matter here. So for example, I'm saying that it's UV. That means I have an arc, which is what we usually call directed edges. But some people keep calling them directed edges too. That's okay. You'll find I typically will refer to them as arcs. It just means that there is an edge that goes from U to V if it's UV like this. So often we call this node the head. The head, and this one the tail. Just think of it like you're pointing it at the other vertex. So some people like to call that the head and the tail respectively. And one other thing is that some people also like to call U. So just for the sake of purpose, some people like to also call this the origin, and other people like to call this the destination. The point is you go from one place and you go to another place. It has meaning in a variety of different ways. For example, when we think about our route map over here, you may, for example, have routes that only go from one airport to another, but not the other way around. That's very often how these directed edges get used. But just to be clear, that when I have an arc that goes from U to V, I can't flip them like I could with an undirected edge. The order is enforced. So if I tell you that if E is equal to UV with the rounded parentheses without any context, then I'm just saying that E is directed from U to V. And I'm also going to abbreviate this with U with an arrow to V to make that a little shorter to explain every time. Are we okay with these two concepts here of the edge types? Because I'm going to do some examples just so that we have an idea of what we mean by these graphs here. Are we all good? Don't be shy. Okay, let's proceed. Whoops. The camera's about to escape me. Okay, so I'm going to just to illustrate my point, I'm going to first take this graph here, and I'm going to, that computer network. You got to get used to doing this, where you look at things and you suddenly see, hey, look, that looks like a graph. Maybe I should think of it like a graph. That's one of those things that computer scientists tend to get obsessed about as soon as they start seeing a structure, especially one that has a little bit more of an inclination like me. You might look at this right away and be like, hey, is there some way I can model this as a graph? That's usually the first thing that you might leap out at. So for example, I can take this same guy here, and I can draw it instead like this. Like say if I make I'm just going to indiscriminately label them. So my servers are going to be V3, V5, and V6. And then I'm going to have my two clients off V6 are going to be V4 and V8. And the clients off of V5 are going to be V7 and V9. So notice that I could take that network and I can represent it as a graph. You can add more meaning on top of this. For example, if we're talking about in terms of the data structures interpretation of a graph, you could, for example, add attributes that guarantee that these nodes are recognized as servers, and then these ones may be recognized as clients. So just to give you a heads up, like you can do things like that with graphs. Just like, for example, when we studied trees, maybe in 210, you may have seen, for example, AVL trees. Oftentimes, we can add a little bit of more information into a node, and it'll help us do things with our algorithms. We'll do the same kind of idea here when we study graphs. So just as an example, let me do one more picture for you. Let's consider the following. Let me draw this graph for you. Here's another one. I get to draw a lot of fun pictures. I'm going to try my best not to make them melt in the microwave. So let's do this. Here's E. And like this. I'm going to make it look like that. That'll look kind of pretty. I can draw all sorts of fun, pretty graphs for you. So you might ask, Dan, what is this graph? So if I were to tell you this is a graph, G, I could tell you that the set of vertices in this graph are A, B, C, D, E, and F. So those are that's my set of vertices. Now, the set of edges, you have to be a bit careful here, because remember, they are pairs of vertices, so I got to list them all for you. Now, do you notice that my edges here, are these edges directed or undirected? Can somebody tell me? They're undirected. So I'm just going to list them as if the order doesn't matter. But like I said, if you ever find yourself saying, hey, look, Dan, I don't like those curly braces, you can always put the rounded ones in. Just make sure when you define this graph, which I'll tell you how you can do that, you just simply assert that before you define the edges. So let's do an example and watch me melt some curly braces. So I have an edge from A to B. Note that you can also say there's an edge from B to A. Note that when they're unordered like this, the meaning for which I used it in a directed edge or arc, it goes both ways. So it has endpoints A and B. Let's see, there's another one. Let's see, you've got AC. So I'm just going to run through all the ones that seem to connect to A. So I'll give a more careful intuition of what that means, what connects means. AC, and then I think I have AF, and then I have AE. Okay, I think that's all of the ones that are connected with A here. Okay, now next let's do the ones with the B. So there's just this one I haven't counted for. There's BD, BD, and I think that's all the ones for B. C, I think I have a CD. Not a literal CD, but CD. And then, of course, that's that one. Then I just have F, where one of the endpoints is F, F, D. So I would say that this is a graph G, well, the VE, where this is the case. If you want to be more precise or more exact, you can say this is an undirected graph because all the edges are undirected. So if you say undirected graph and then you start putting rounded parentheses, that's okay. I just want to be clear. Very nice, very nice. I like that. I like that. So now this would be an example of what we call an undirected graph. Notice every edge in here is undirected. That's why we call it that. But notice that, is everybody fine with this example? I just want to make sure we're clear with our terminology. So every one of these circled entities here. Those are what we call the vertices. And the edges are the connections between the vertices. Note that there's a lot of different ways you can connect edges with vertices, but this is a common way we can do so. I'll talk more about that in a moment. I'm just going to get rid of my computer network. I'll leave that picture there. Okay. So let's proceed. So there's several different kinds of graphs. There are several kinds of graphs. So there are several kinds of graphs. I already alluded to the first main kind, and usually when I don't say anything, I usually just assume that this is what you mean. So if I don't quantify anything more specific, I'll just assume that it's an undirected graph. So an undirected graph is quite simple. It's a graph with only undirected edges. So it's just a graph with only undirected edges, where all the edges are going to be undirected. That's why we call it an undirected graph. Now you might guess what a directed graph is then. Sorry, I get really excited about this. So if it's a directed graph, now some people like, by the way, some people like to call these digraphs for short. So they call it a digraph. So this is just simply a graph where all the edges are directed. And you might ask, what can you do when you have like a combination of them? This is what we often will call a mixed graph. So a mixed graph is where some of the edges may be directed, some of them are undirected. It's a mix, right? It's like I have like a taco salad. So let's see. It's a graph where edges. I know I'm terrible. I'm sure somebody heard taco salad and is just like, man, I would like some right now. Are directed. And if I might be more precise, where a graph where edges are directed and undirected. So I mean that some of the edges may be directed, some may be undirected. Not that they're literally at both times, just to be clear, because it just makes no sense. I do want to point out one thing, just as a remark, is that if I wanted to represent any undirected graph, I can do that with a directed graph. If you think about it, so imagine I give you an edge like A to B, where the endpoints, the endpoints of this edge E are A and B. You might ask, Dan, how can I represent this undirected edge as directed edges? Well, one common way you can do this is you can replace the single undirected edge with two directed edges that go both ways. So now I have two directed edges. I can replace the undirected edge like this. But I must warn you, this is one very important detail I must stress, speaking as somebody that studies these kind of problems. Careful, you may lose the meaning. You may lose the meaning of the model. So technically, like I said, you can convert undirected graphs into directed graphs. So you'll find very often I can just say a lot of things about undirected graphs, and then they generalize over directed graphs in some ways, in some contexts. But you have to be careful, because when you're studying a problem, and say these undirected edges represent something very special, and if you switch it with two arcs like this, you may actually destroy the meaning of what it means in the original graph. or it may have a completely different interpretation. So I just want to point that out. So if you find yourself curious about this construction, take this picture in your spare time, take this graph, and turn it into a digraph by simply replacing each of these undirected edges with a pair of directed edges. So if you ever find yourself saying, oh shucks, I need to give you a digraph, but I have a undirected graph, that's an easy way you can convert it over. So that thing I do need to stress, but I must stress the other direction isn't true. For example, you could have it where there's a directed edge that goes this way. There's no simple way for me to just simply replace this with an undirected edge. The direction of the logic only goes one direction. I just felt like mentioning that. That's more of a remark than anything. So I want to talk next about the concept of adjacency. So first, are we okay with the terminology so far? Am I clear? Don't be shy. I like questions about these things. I dream of graphs. Okay, I think we're good. So I want to talk next about adjacency. So I've been always saying like, okay, well, the edges are connected in some way, but I need some formal way to actually say that, because being connected is somewhat informal in a graph theoretic way, because what does connected mean? Well, we assume when we hear that, I'm talking about, okay, there's this edge here that connects these two endpoints, right? That's what I think about when I think of that they're connected. But there's actually a couple different ways we can think about connected. You can think about it as, oh yeah, this one's connected to this one by this edge, or you may even talk about the edges being connected. You can say that this edge and this edge are connected by this endpoint. There's a couple notions of talking about notions of connection. So I'm going to talk about adjacency first. I changed that from adjacent to adjacency because Wednesday makes it fun. So just to be a bit informal first, there is an edge connecting, put that in quotation marks, connecting two vertices. There's an edge connecting two vertices. So I'm going to break this down into two cases where I'm going to talk about in an undirected graph, then a directed graph, or vice versa. So just I'm going to keep things broad first. I'll use the rounded parentheses just more broadly first. Then I'll say, okay, in a directed graph, this means blank. In an undirected graph, this means blank. Just to be clear. So if edge UV is in a graph, if edge UV is in a graph, then vertex V is adjacent to vertex V, vertex U, getting ahead of myself. So that's the phrasing we will use if I want to talk about saying, oh yeah, no, I want some way of saying that these two vertices A and B are connected. I'll say that A is adjacent to B, or B is adjacent to A, for example. So I just have a couple of cases I need to knock out for this. Let me move over to that board, because you have to be a bit careful, because remember, if I have directed edges or arcs, the notion of adjacency changes ever so slightly, because you got to think about it almost like the arrow prohibits you from going the other direction if it's not pointing in your favor. But in an undirected edge, it really doesn't matter. Remember, the order doesn't matter. So I have to make sure I kind of break this part carefully for you. So in a directed graph, B is adjacent to U if you have an arc that goes from U to V. So V is adjacent to U if there's an arc that goes from U to V. So I have an example in the notes. I encourage you to take a look at it if this notion, it seems a little strange at first. So if that's the case, that's for directed graphs. I must stress that adjacency in directed graphs is not symmetric. Like I said, it depends on which way the arrow on the directed edge is pointed. So if you want to have it where it is symmetric, you need directed edges going to both directions. You have two directed edges, just like in my example I had over there, where I took that undirected edge and I turned it into two directed edges. That's when you can have it where you have it symmetric, where you can kind of say, oh, V is adjacent to U, or U is adjacent to V. But that's literally how we're interpreting an undirected graph. So in an undirected graph, G, an edge, UV, in G implies, like I said, implies U is adjacent to V, and V is adjacent to U. So you don't have to be picky about how you phrase this. Is adjacent to U. So, like I said, it's symmetric for undirected graphs. So I can replace them, I can swap them. It doesn't matter. So that's adjacency in a nutshell. Are we okay with the notion of adjacency? So this is a way I can talk about if I want to say this vertex and that vertex, I want to know, are they connected by some edge? This is the way I could do it. I could talk about adjacency. Okay, so if we're good with that, let me move on to incidence. So let's talk about incidence. So this is the other notion of connected that I alluded to. So there's this thing called incidence. So we say two edges, E and E prime, are incident if at least one endpoint E and E prime is the same. And when I have this happen, I'll say that E is incident with E prime. That's the phrasing I'll typically use. So if I want to talk about two edges, and I say that there is at least one endpoint that's in common between the two, then I can say that E is incident with E prime. Furthermore, this incidence idea also gives you another clever way of talking about the relationship between an edge and its endpoints. Furthermore, in an undirected graph, edge UV, so this is an undirected edge, right, is said to be incident on, so notice I'm using the phrase incident on, vertices U and V. So now I have a way I could talk about with incidence. I could talk about two edges having a common endpoint. Or I could say that, okay, if I give you some edge, there is going to be an endpoint on one of its two sides, right? I can talk about those endpoints with respect to an edge this way. So for example, if I give you an edge, say E, and its endpoints are A and B, I could say edge E is incident on B. Or I could say edge E is incident on A. So it's a nice, clever way of shortening things down if you really need some way of simply saying it. Now, in a directed graph, because I always have to talk about these two, an edge, UV, is incident from. So this direction thing actually creeps in here. So it's incident from. Let me switch my marker. This one's being a little funky. So in a directed graph, an edge, UV, is incident from. Is incident from. Sometimes people say it leaves. Just be aware of that. Incident from vertex U. And is incident to vertex V. So this is to from relationship. Man, the tail on that U really got long. Let me fix that. It's having a long day. So in a directed graph, an edge UV is incident from vertex U and is incident to vertex V. So this is the, yeah. So I'm going to show you an example of what I mean by this. So let me just, actually, I have it right here. Let me modify this picture here that we have, and I'm going to draw an example for you. So I'm just going to take the same graph, and I'm just going to turn it into something else. I'm going to change what this graph represents. So just remember, this is not the same graph I had before. So I'm going to add some arcs in. Let's say we do this. If you want more instances with this example, I have it in the notes. But let me draw. So here's an example of a directed graph. So here's a directed graph. So if I want to talk about this a little bit carefully. So if I were to talk about edges or arcs, AC. So if I talk about AC and CD. So actually, no, let's talk about the directed graph first. So let's talk about the directed graph. Sorry, AC and say AF. Notice that both those arcs are leaving. So both of these arcs are leaving vertex A, right? So we would say the following, that it's incident from A, and I can also say other things. So notice I could say it's incident from A, and then I could say, okay, well, then it's also incident to C. If I'm talking about the arc from A to C, I can also say, oh, it's from A, and it's also incident to F. Then you can also say other things such as, say, for example, D, if I consider this directed arc right here, and I could say that the directed arc, sorry, my arc, I'm getting a little ahead of myself. The arc DC is incident to vertex C, because notice this is where the head of the arrow points. So I know that's to as opposed to from. So that's the relationship with incidence when it comes to directed graphs. Undirected, remember, all it is if I were to give you just say this edge right here, and I say added another, actually let me move over the camera now, because I don't need to be over there anymore. So say if I have another graph like this, A, B, and C, like this, and say if I have edges E, E prime, and E double prime, I can say that edges E and E prime are incident with each other, right? So E and E prime are E is incident with E prime. Sorry, I'm getting really excited here. All right, so That's one way. You can talk about the width relationship, and you can also say, okay, well, edge E is incident on C, or E is incident on B. But notice that the relationship, so adjacency talks about the connections between the vertices. Incidence talks about the connections between the edges with respect to the vertices. Is that clear, everybody? So those are two notions of connectedness between endpoints. I'm going a little slower because I just want to make sure I'm being very careful with the way I talk about the terminology. Because I'll be using this terminology for probably the rest of this month. So there's a notion of adjacency and there's this notion of incidence. I've also included, I think there's another example in the notes. That's basically this picture. If you say want to really play around with this a little bit more. This section is going to have a lot of fun pictures. So, okay. So the next thing I want to do is also define the following concepts. So you notice that when I put an edge in, notice that I don't have multiple edges between two endpoints, right? I only have one. So this is what we often call a simple graph. So if you're wondering, if ever I talk about a simple graph, these are normally what I'm just going to presume are what I'm going to talk about unless I say more. So this is a graph with with no, what I'm going to call multi-edges, which I'm going to define in a moment, with no multi-edges or self-loops. Another thing I'm going to define in a moment. So suppose I give you a graph that looks like this, A, B, and these are undirected edges, by the way. What I can do is I can actually have it where I can put multiple edges between two vertices like this, so that each one of these edges has endpoints A and B. So that's an example of a multi-edge. So these are what we call multi-edges. And notice that I can actually put an edge and warp it back to the same endpoint. So its endpoints actually are the exact same vertex. So there's only one, there's really just one unique endpoint of this. This is what we call a self-loop. And these, when I have more than one edge between two vertices in this sense, we often call these multi-edges. So when we don't have multi-edges, meaning there's only one edge between two vertices, as in that edge is incident on its endpoints, there's only one such edge, then we would say that the graph is simple if it doesn't have both of these things. That's how I'm going to define simple graph for you. So just to be clear, so a self-loop is an edge whose endpoints are the same. And of course, when I talk about multi-edges, sometimes people call these parallel edges. That's also okay. Multi-edges or parallel edges. The reason why I call them parallels, you know, it's like I can look at them like they have both the same endpoints, but I can add them, I can stack them, I can have as many as I like. You can think of them like a bunch of straight lines. So you can think of them like lines that are parallel. I just drew them that way because it makes it more fun. I must stress that the way I draw these doesn't really matter too much, at least in the context we're using them. So these are multi-edges or parallel edges. So this is where two or more edges with the same endpoints. With the same endpoints. So that's what I refer to as a multi-edge. It's just that I'm allowed to have more edges between the same endpoints. And of course, that means I have to define what is called a multi-graph. A multi-graph as opposed to just a graph. You might guess what the definition of a multi-graph is. A multi-graph is very simple. It's just is just a graph that allows multi-edges and self-loops. Now, some authors, they like to make this part about the self-loops optional. I'm going to say, yeah, you're allowed to have multi-edges and self-loops. Typically, it is the case that both of these are allowed in a multigraph, but some authors, so if you pick up a random graph theory book, some people will define multigraph to have only that it has multi-edges, not necessarily self-loops. But this is how I'm going to assume the definition, just to be clear. So just to be clear what I said earlier, unless otherwise stated that D has a little bit of a tail. Unless otherwise stated, the graph will examine always is simple and undirected. So unless I add quantifiers like, oh, it's a directed graph or anything like that, just assume it's always simple and undirected if I don't say anything. If I just say it's a graph, that's just make the assumption I'm talking about that. So when we come back next time, we're going to talk a bit more about properties graphs have and different kinds of structures we can talk about with respect to graphs. So that being said, I'll say thank you very much and have yourself a beautiful day. I'll see you later.